few evaluation test setups just to get a feel. So how does the environment change? How does the measurement result change when we go from conducted to over the air? And we just did it on 4G devices that is available, there we know what to do. And then where are we standing at 3GPP, especially when it comes to over the air testing, as you might have realized, which is one of the topics I'm interested in. Okay, 5G is on its way. I'll just go across that slide. I think we all know this, and the ITU World Congress is now almost 2 years ago. So, but this is basically the ITU timeline, but what I think is more important for us is the 3GPP timeline. And this is where we stand now, 2017, end of April, the TSG REN 75 was in March, and the release 14 was completed, and also the new radio study item was completed. And there's already some findings out of that, and there will be additional work. So for example, one important note that's hidden here on the bottom left corner, so new radio will interwork with LT only and not with G-RON or U-TRON. I think that's an important statement, but we know that the coexistence is absolutely necessary, and we have some topics about their 5G non-standalone, which is in conjunction with the sub-6 GHz LTE carriers, and then only in the second phase of the standardization, which is coming in release 16, we'll also look at the standalone approach for 5G NR. So, as you can see, NR has been split into 2 phases, and it's been constantly accelerated. So we see a tendency that with every meeting there's another attempt to accelerate the standardization work and to get to results much quicker than initially planned. So there you can see that the naming convention, so from 3G U-TRON we moved to enhanced U-TRON, and now we're at NR, which is the new radio. And the application scenarios is also something that's probably being discussed, enhanced mobile broadband. I think we know what it is anyway, that's what we've been doing all the time. Interesting little side note, the massive machine type communication has been put a bit on the back burner in 3GPP, so they don't accelerate that so much. And then the ultra-reliable and low latency communications, interesting to see, as in all the other forums now we see the automotive industry very getting involved, and especially on that URLC approach. And obviously the frequency very widely spread, and as you can see as well at the bottom line, there's still a lot of TBD. So, and I think we had this discussion earlier today, we don't really know what's happening in detail, and this means that we have to be ready for almost everything. I guess it's something we all in this room here have to face and have to cope with and have to go ahead with. So this is the spectrum outlook. I wasn't following Rainer's presentation, I don't know what he had, but I mean we're already looking at 30 gigahertz of total available bandwidth, but we're also talking all the way up to 86 gigahertz, so that's from the World Radio Congress from ITU. What I think is interesting is the last sentence here, the 28 gigahertz band is not fully covered. But I mean, we all know, especially here in this occasion, how important it is. And there's been a very interesting decision in Europe. Apparently the satellite industry or satellite network providers have a stronger lobby in Europe than here, because Europe ruled out the use of that spectrum for 5G because of the usage for satellite communication. Yeah, and just a little reminder, it's more for your reference and future looking into the presentation, which frequencies, wavelengths we're looking also, but also a very important one, and I think that follows nicely to your presentation from earlier, so our free space path loss, and how we have to counter that in the applications if we go at just at centimeter wave already at 30 gigahertz, where we're speaking about 62 dB a meter. So how, for conformance testing, for certification testing, how can we replicate this test setup? This is what we do. This is our basic conducted LTE certification setup for UE. And we've got our UE on the test on the right side, and then we've got some red line, and where we have the interface to the test system on the left. We've got the downlink simulation from the test system, which we have here on the left. We've got ideal conditions in the uplink. And we have a very clear reference point, which is here at my device on the test, here at the antenna connector. And now we all have to face the situation that this will not be the case anymore. Now we have antennas. And it's just simplified, it's just 2 antennas here, or it could be whatever we come up with, but how do we actually measure that? What are the real challenges when we go into something that needs to be reliable and repeatable test setup? Because as I said before, we're going to do certification and conformance testing, where it's not only characterization, but absolutely repeatable. And we introduce the antennas, obviously. We have crosstalk. We will have maybe 2x2 only in this case, but we have crosstalk from the antennas. My topic from earlier, from the earlier presentation, when are we in the near field, when are we in the far field, where do we actually need to be in comparison to literature or to what's actually happening, what's our reference point. Pretty sure we need an anechoic environment. You were asking the question before, anechoic or reverb. And how do we maintain that ideal uplink? So all these questions that are currently under consideration, but certainly not answered yet. And what's also happening, we've got another dimension we have to look at, or measurement domain, measurement dimension, which is space. And we've got the time domain, we've got the frequency domain, and the code domain. We always got our desired result, and we've got some limit line. But what we also have now is we've got, for example, power depending on the direction of departure of the signal. So we need to define limit lines here as well, and we need to actually cope with that, because what we see in that small test setup we have, it matters how you measure this, obviously, and how you turn this device during the test. Whereas in the past, with an ideal connection, that was easy. So what we did here is we used, again, an anechoic environment. We've got a 3D positioner in there, and we used a known device with our communication tester and our software. We automated the testing for TLP and TIS, and also did then some signal quality measurements in this setup. So what was important to us is we've got a stable reference environment with an anechoic chamber, and we also have the possibility to move the device on the test. As I was stated before, we've got a 4th dimension now, which is space, and we can already see here in these simple results that it does make a difference. So what do you see here? We use that picture of the die, or a cubic device, which just shall simulate the 6 positions we can put our device on the test into when we measure it. And we just did these 6 positions. So display side, 90 degree, turn right, and so you can see that reference here. And then we measured, you can always see the blue line is the left-right polarization, and the front-back polarization is the red line. So these were the over-the-air measurements of a known device. And as a comparison, we have the cable measurement, which is the green line. That's our conducted measurement of a known device, and now I wanted to see how does that compare the ideal setup of the device we know. So the green line, for example, when we look at the invent spectrum mask, you can see, for example, for the position 1, this here doesn't add up at all, what we have there. And you already see that there is a preferred site for the device on the test. Maybe if we look at and that it's polarization dependent as well. So if we look at position 2, red line and green line, they intersect pretty well. So there we've got a good match. And on position 6, we've got the same with the green and the blue line. But it is position dependent. So how can we define a test setup? How can we define the limit lines and make sure that it's a repeatable test and that it covers all the different circumstances our device will be placed under in the real life? And we did a similar thing for EVM measurements. So the same 6 positions, and here you can see the green is the conducted measurement of EVM, and the blue is the over-the-air measurement for in the left-right polarization. And again, you can see that in position 3, there's a big distance. So how do we actually put it in the standard? How shall we measure the device? How can we characterize it? Is that something where, just as for active antenna systems, we can choose, or the manufacturer can choose his preferred size, just like the manufacturer declared beams for AAS? And is it maybe just in one direction, or how do we need to look at it? But again, it shows big differences at the position 4 as well, or 1 to 4, and maybe closer to between the conducted and the over-the-air test setup at 5 and 6. Again, we can see the overall tendency that, as expected, the EVM values are higher for the over-the-air case than for the conducted one, for the ideal conditions.